Alright, this is additional example set number 2. Question 1. From a committee of 7 people, a chair, a secretary, and a treasurer must be chosen. In how many ways can these 3 people be selected? Alright, so number 1. So I need to select from 7 people. I need to select 3, and I have to assign them to different titles: chair, secretary, and treasurer. So one way I can do that is by saying step 1, select the people first, and then look at what I have to do next. So in how many ways can I select 3 people from 7? 7, choose 3. For example, let's call these people person 1 to person 7. For example, what do I have at the end of step 1? I just have 3 people floating around in no particular order. I just selected 3 people from the 7. What do I actually have to do? In order for them to be assigned the specific titles, how many ways can the chair be selected? 3 ways. And how many ways can the secretary be selected? 2 and 1. So if I arrange these people in a row, the first one could be the chair, then the secretary, and so on. So I'm actually looking for an arrangement of the 3 people. Arrange / assign them to their titles. In how many ways can I arrange them? There are 3 of them, they're different, 3 factorial. So the total number of ways to make this assignment of 3 people to their titles is 7, choose 3, 3 factorial. In question number 2, a group of 20 friends, 10 men and 10 women, go to an amusement park for the day. A. The haunted house allows only 5 people to enter. In how many ways can 5 of the friends be selected if the selection should have more men than women? So now I have to look at number 2 and say, okay, I have a collection of 10 men and 10 women. I need to select 5 of them. Just make a selection. There's no mention of arranging or anything. But I have to have more men than women. How can that happen? Let's just think how that can happen first. How? I can have 3 men and 2 women, or I can have 4 men and 1 woman, or I can have 5 men and 0 women. And in all 3 of these cases, in each of these cases, I've made a selection of 5 people. I've completed my experiment. But there are 3 different ways to complete that experiment. So, in how many ways can I select 3 men and 2 women? Choose the men, followed by choose the women. In how many ways can I choose 4 men? 10 choose 4. And 1 woman, 10 women, choose 1. 5 men and no women, out of 10 men, choose 5. And for the sake of consistency, I'll write here, out of 10 women, choose none. This represents the number 1, so you can opt to leave it out, you can write it in, it doesn't change anything. So how do I put these together to get my final answer? Well, if I'm doing this as step 1 and then step 2, step 1 selecting 3 men, step 2 selecting 2 women, am I done? with my experiment? Yes, I've selected 5 people, and that was my goal. This is another way, and I start the experiment following 2 steps, finished. 3 different ways to satisfy the restriction, so I have to add them together, and then I'm done. Now this was part A. Let's look at B. The friends want to sit down to watch a show, but there is only 1 row of 8 seats available. How many seating arrangements are possible with some restrictions? So now I have 10 men, 10 women. My experiment has changed. I am selecting 8 and arranging. So I'm trying to arrange 8 people in a row. First restriction is only women are allowed to sit. So we can always list this as step 1 and step 2 and so on, or we'll do the steps in one line. So what is step 1? Think, select and arrange. How should I select my people to satisfy the restriction that only women are allowed to sit? Only choose from the women, 8 women from 10. So this is the select, followed by I want to arrange them. That's my new experiment. How can I arrange them? Is there any restriction on the arranging? No. So I multiply that by 8 factorial to arrange them. Second one, it says at least 1 woman should sit. Now there's multiple ways to do this. One way is I can think of this directly. And how many options do I have if at least 1 woman should sit? I can have exactly 1 woman, or exactly 2 women, or exactly 3 women, because at least 1 means 1 or more, all the way to exactly 8 women. There's a lot of cases. There's a lot of writing down. Even though I can totally do them and add them together, when I have that many cases, I should consider the complement. Is that maybe a faster way, a more efficient way of doing it? What would the complement be? Well, I have 1, 2, all the way to 8 covered, so 0 women. That's the only case that's not covered. So what I would do here is, let's write it indirectly first. We'll take no restriction minus 0 women sit down. So I take absolutely everything, take it away, take away from that all the cases that I'm not looking for, and what I'm left with has to be what I'm looking for. So no restriction, I just have 20 people, I select 8 and arrange, minus the number of ways to select and arrange 8 people, but no women. So select just from the men and arrange. Let's do number 3 up here. Number 3 now says John and Jack sit down, but not next to each other. Now there's more than one way to do this. This is one way. So again, I know I want them to not sit next to each other, but I know keeping them together is easier, so I'm going to think indirect approach. So the number of ways to do this, let's go to our basic indirect approach where I take no restriction. Now what do I take away? I take away where John and Jack sit together. I don't want that. But when only one of them is selected, I also have the restriction satisfied that they don't sit next to each other. And if this is the only thing, the only case that I'm taking away, I have absolutely everything. Take away where they're both selected and they sit down. In here, I still have, if I leave it like this, I still am counting the ones where only one of them sit down and not the other. And that's not the restriction. The restriction technically has two parts here. I need them both to sit down, but not next to each other. So I need to be sure that I take away not just the part where they sit together, but also the part where only one of them is selected. So let's say here, only one of them sits down. So this is another thing that I have to be careful of. I have to understand the restriction very clearly to make sure, yes, I'm going to do the indirect approach, but am I subtracting everything I should? And in this case, the restriction comes in two parts, so I have to be a little bit more careful. Okay, so now the number of ways to do that. Well, no restriction is 20, choose 8, and arrange the 8 people. Subtract, John and Jack should sit down, so I'm going to select John and Jack. Then out of the 18 other people, I need 6 more. Now that's my selection phase. Done. I have to follow that by arranging them in such a way that they sit together. So I'm going to glue them together, John and Jack, person 1, person 2. How many other people do I have? 6. So I have 1 and 6 more. I have 7 people to arrange, and I can arrange inside the super person, so to speak. Now I also have to count the number of ways where exactly one of them sits down. First of all, which one? So here, what I'm doing is I'm choosing John or Jack. I can choose one of them to sit, and that one will sit. Out of the remaining 18 people, I have to choose 7 more. Now I have my 8 people. I don't care how they sit, because by selecting one of them, I have no issues that they'll sit together. So I can arrange them in any way possible. So this one is a little bit more complicated. I have to make a plan first. I see that I want to do the indirect approach. Am I subtracting everything so that I only get what the restriction wants? So the next question is number 3. You're at a party with 19 other people where everyone wishes to meet everyone else. In total there are 10 men and 10 women. How many meetings are possible? So number 3A. So the key here is to see that there is one meeting for every pair of people. So you have 20 people in total. You want to select 2 of them, and there is a meeting between them. So the number of ways you can do that is the number of ways you can select 2 people from 20. 20, choose 2. And B, they say how many meetings are possible between people of the opposite sex, so men and women. Again, now you have 20 people, you want to select 2, but you want to select 1 man and 1 woman. How many ways can you do that? Well, I have 10 men, choose 1, 10 women, choose 1, done. Step 1, choose a man. Step 2, choose a woman, and you're done. In number 4, From a group of 8 men and 10 women, 5 men and 5 women must be selected and seated in a row. So I'm looking at arrangements. How many different seating arrangements are possible if I have some restrictions there? The first one is no restriction. So in number 5, I have a collection of 8 men, 10 women. I need to select 5 men and 5 women and then arrange them in a row, and there's no restriction. How many ways can I do that? Well, think select and arrange. I have 8 men, I'm choosing 5. I have 10 women, I'm choosing 5. And how many ways can I arrange them? There's no restriction on the arranging, so 10 factorial. That's A. In B, the sexes must alternate. So now, how can that be done? How can that be done? Well, I eventually have a row of people. It can either start with a man, then a woman, then a man, then a woman, and so on. Or I can start with a woman, then a man, woman, man, woman, and so on. So it's this way or the other way. 2 different cases to get me that restriction. If I look at this one, how many ways can that be done? Well, I still need to select out of the 8 men 5, out of the 10 women 5, but now what? Now I have a restriction on how I can arrange them. It has to be man, woman, man, woman. So the men are fixed in their positions, but I can shuffle them among themselves, 5 factorial. And the women among themselves can be arranged, 5 factorial. This one, again, select 5 men, 5 women, arrange the men among themselves, arrange the women among themselves, because the positions of the men are fixed, the positions of the women are fixed. So, the number of ways, the total number of ways to do this is case 1, this is case 2, so I add them together. First one plus second one. In this case they happen to be the same, but I'm adding them together. Different ways to get the restriction. Of course, this example is not number 5, it is number 4. Number 4. Let's do number 5. You are packing for a long trip and you want to bring some reading material. You want to arrange 4 books in a row in your suitcase. There are 18 different books sitting on your shelf. 12 are fiction and the others are non-fiction. If you randomly select 4 books to arrange, what is the probability of getting some restrictions? The first one is you have alternating fiction and non-fiction books. So this is number 5. Now let's set this up. You have 12 fiction and then of course 6 non-fiction. You are selecting 4 and you're arranging. And now I want to know what's the probability of getting alternating fiction and non-fiction. So in A, let's just see how that can happen. I can have fiction, non-fiction, fiction, non-fiction, or I can get non-fiction, fiction, non-fiction, fiction. So there's 2 basic ways to get that. For a probability, let's define E as the desired event, just giving it a name, just a formality, so I can talk about the probability of E. Bottom first, no restriction. I have 18 books, choose 4 and arrange. Now the top, I'm going to follow these 2 different cases. First one, well, I need to select 2 fiction books, 2 non-fiction books, but their positions are basically fixed. I can just shuffle the fiction among themselves and the non-fiction among themselves. Or a completely separate case, so I'll add that number, select 2 fiction, select 2 non-fiction, arrange them among themselves for the second case. In B, there are more fiction than non-fiction. How can that happen? Well, I can have 4 fiction and 0 non-fiction, or I can get 3 fiction and 1 non-fiction. The next one is 2, 2, and that's not what I'm looking for anymore. So let's call this event F, the desired event, so that I can talk about the probability of F. Bottom is still the same, no restriction. Choose 4 books, arrange them in any way. I'm going to follow this 2 cases again. So now I want 4 fiction books. I'll write here 0 non-fiction and arrange them. Or 3 fiction, 1 non-fiction and arrange them. I'll go to a new page for C. And C says there are only fiction books. So let's call this event G. The G represent the desired event, so that I can talk about the probability of G. No restriction at the bottom, same as always, it's the same experiment. Now I want only fiction books. So out of the 12 fiction, I choose all 4 and arrange them. Done. D. D is at least 1 fiction book. So you can decide, you want to do it directly or do you want to do it indirectly? Let's do both, because we're trying to practice. Directly, we can have exactly 1 fiction book, or exactly 2 fiction, or exactly 3 fiction, or exactly 4 fiction. All of them are fiction books. That's not bad, it's only 4 cases. It's not terrible. It's not terrible. Indirectly, we would look at no restriction, take away everything that's not covered by the restriction, which is 0 fiction. So you can choose which one do you think is more efficient. This one for sure, but there's nothing wrong with the direct approach either. Regardless, let's call H the desired event. Then the probability of H, let's do the direct approach first. Bottom is still no restriction, same as always. Exactly 1 fiction book. Well, out of the 12, select 1. Out of the 6 non-fiction, select 3 and arrange. Or, so plus, out of the 12, select 2. Out of the 6, select 2 and arrange. Or 3 fiction, so out of the 12, select 3. Out of the 6 non-fiction, select 1 and arrange. Or all 4 fiction, out of the 12, select all 4 fiction. And you can say here, out of the 6 non-fiction, select 0 for consistency's sake, and arrange. Extend my line to show this is the top, that's the bottom. I could have also said the indirect approach, so this is direct, and this is indirect. multiple ways to answer the question. Now I take no restrictions, so I have 18 choose 4 factorial, which this bottom is, minus no fiction. So I choose no fiction books, all non-fiction, and the range. And these two will be the same number. In number 6, a bag contains 40 numbered balls, 10 of which are blue, 10 red, 10 green, 10 yellow. 5 balls are randomly selected from the bag so that every selection is equally likely. What is the probability that the selection of 5 balls, then I have some restrictions, contains only green and so on. So we're looking for a probability. So let's see. We have 40 balls, so that's number 6 here. 40 balls, 10 blue, 10 red, 10 green, 10 yellow. And I want to make a selection of 5. Just a selection. They're not saying anything about arranging. So in A, I want only green balls. Let's call that event. Let E represent the event that they're asking for. So I'll just say let E represent the desired event, so that I can then talk about the probability of E. Now remember, that is the number of ways to get that restriction divided by all possible ways. So bottom first, without any restriction, how can I select 5 balls from 40? 40 choose 5. That's a 5. How can I get only green balls? Well, I have 10 green balls. I want to select 5 of them and I'm done. In B, contains at least 2 red balls. Well, we haven't done anything directly yet, so let's do this one using the direct approach. Let F represent the desired event, so that we can talk about the probability of F. Same experiment, so the bottom will be 40 choose 5. Now how can I get at least 2 red balls? I can get exactly 2 red balls, so select 2 red, and then 3 other balls, or, so plus, I can get 3 red, select 3 out of the 10 red balls, and 2 other balls, or, so plus, I can have 4 red. Out of the 10, select 4 red balls and 1 more other ball. Or 5 red, all 5 red. Select 5 red balls and nothing out of the other 30. Just to show you that the direct approach, there's nothing wrong with it in most cases. A little more writing, but it doesn't matter. I could have also done the no restriction minus the complement, and in this case that would be 0 or 1 red. And you can argue that's a little bit less to write down. No restriction would simply be 40 choose 5, as the bottom is, minus, but now there are 2 cases here, so I'll put that in brackets. 0 red, so select none of the red and all 5 out of the remaining 30, or 1 red and only 4 other balls. As long as you have those brackets, everything's going to be fine. The last restriction contains all 4 colors. All 4 colors. Let's call that G to represent the desired event. probability of G over 40 choose 5. I want all 4 colors. Well, I'm selecting 5 balls, and there are exactly 4 colors. So before I rush to writing down the numbers, something choose something else, I need to think about how this can happen. Is there more than one way this can happen? What is the color composition? Because I'm selecting more balls than there are colors. So how can I get all 4 colors? Let's do it on the side here. I can have a color composition, 3 of the same color, and then 1 each of another color. Is that going to work? Totaling 5. Do I have all 4 colors here? No. I can have 2 of one color and 1 each of the other colors. Is that going to work? Giving me 5 balls in total, every color is represented. That seems good. And I can't get anything else. But sometimes it's worth thinking, just, is there more than one way to do this? In this case, it seems like there's only one basic color composition. In terms of one color is going to get repeated, 2 of them, and the others will be singles. Now, in following steps to construct your answer at the top here, let's make an example and try and be aware of what you're deciding on first in making an example. Let's make an example, or pause and make your own example. My example could be red ball 1, red ball 2, and then I stop. I had to decide which color will appear twice. I chose red, but that's not the only choice. And that tells me what step 1 should be. Choose the color that will appear twice. 4 colors, choose 1. Choose the color that will appear twice. In my example, that's red, and that then fixes all the other colors to be singles. Now I choose the 2 specific balls out of that color. 2. And then green 7, blue 3, and yellow 5. 1 of each of the others. And I'm done. But by making an example, checking how I can get what I'm looking for, make an example, stop and be aware of what decisions you've made in constructing the example. That tells you what steps to follow. So let's do number 7. 2 balanced dice are cast. One is a 6-sided die with faces labeled 1 through 6, while the other is a 4-sided die with faces labeled 1 through 4. Let x be the positive difference between the result on the 2 dice. Determine the probability distribution for x as well as the expected value of x. And this comes from section 1.7. So okay, now this is number 7. Now we have 2 dice. One is a 6-sided die, so that'll have numbers 1, 2, 3, all the way to 6. And the other one is a 4-sided die, just to make it a little different, so that'll have numbers 1, 2, 3, and 4. Now I'm looking for x is the difference between the 2 numbers that I get when I roll these dice. And I'm only taking the positive difference, so always the bigger one minus the smaller one. So now I have to look at what are the possible values of x. Possible values of x. Well, what is the smallest difference that I can get? Well, it's going to be when the two numbers are the same, the difference will be 0. And the two numbers are the same. For example, if I have two 2's, then the two numbers will be the same, the difference will be 0. Can I get a 1? Yes. For example, when I have a 2 and a 1, the difference is 1. I can get a 2, and so on. What is the largest difference that I can get? Well, that'll be when I have a 6 on die 1 and a 1 on die 2. So the largest difference will be a 5. If I have a large number here, anything there is going to be less than 5 in terms of the difference. Bigger and small, biggest one here, smallest one there gives me the biggest difference. So I have numbers 0 through 5. And now the next step is to find the probabilities for each of these 6 values of x. So I can do that separately, or I can do that as a table. To state my probability distribution, I could say let's have the different numbers, and then I'll have the probability that x equals that number. So the number 0, what is the probability of getting 0 as the difference between two numbers? That is just another way of asking, what is the probability of getting two of the same number? So now in this case, I would have to have 2 1s, 2 2s, 2 3s, 2 4s. There's only one 5 and only one 6. So in how many ways can I get that? I find with dice problems where I have 2 dice usually, it's almost simpler than having a fancy counting argument to just make a list of all the possibilities and count how many there are. Clearly there are 4. So 4 out of a possible, how many? 6 possibilities for the first one, 4 possible numbers for the second, so 6 times 4, or 24. So in this case, it might be simpler to just list all the possible pairs of dice values that I can get and count them. Not to overthink dice problems like this. Now the next one is the probability that x equals 1. In other words, that the difference that I get is a 1. So I'll have some rough work over here just to see all the possibilities that I can get. So let's say we have die 1 and then die 2 as a pair. How many possibilities, how many pairs will give me a difference of 1? Well, I have 1, 2, 2, 3, 3, 4. Now this is die 1 and this is die 2. So the second one only goes up to 4. Or I can have 2, 1, 3, 2. That's different because now die 1 is a 3, die 2 is a 2, different from this one. And I can have 4, 3. Now this one can go up to 5, 4, but not any higher because the second die is limited to a 4. So I have 1, 2, 3, 4, 5, 6, 7. So I have 7 out of 24. So I just go down the line like this, and now I'm done with these. So now the difference should be a 2, and it's going to become easier as I go. So start small with die 1, 1, 3, 2, and 4. Can't go higher with die 2 than 4. It only has 4 options. Or I can swap them around and have a 3, 1, 4, 2. Now I can go higher. 5, 3, 6, 4. 1, 2, 3, 4, 5, 6 possibilities. And I keep going like this. I might have to do the table over here, but still. 3. How can that happen? Now I'm looking for a difference of 3. So start small with die 1, 1, and 4. That's the only one, because I can't go up higher with die number 2. Swap it around, where die 1 is the larger one. 4, 1 gives me a difference of 3. I can also have 5, 2 and 6, 3 because die 1 can go higher. So it seems like I have 4 possibilities out of a possible 24. I can squeeze it in here, 4 and 5. 4. Now I want the difference to be a 4, so I can't do much with the die 1 being a number 1 because I can't get die 2 high enough. So my only option is if die 1 is 5 and die 2 is 1. So I have 1 out of 24. Now let's see. So far, how many do I have here? 4 plus 7 is 11, plus 6 is 17, plus 4 is 21, plus 1 is 22. Am I missing anything here? Let's leave it for now. Let's suppose, I'm doing this on purpose, let's suppose that this is all we saw for a difference of 4. Now I go to a difference of 5. How many ways can I get a difference of 5? Well, 6, 1 is the only possibility that I can get. So there's only 1 there. Now I add these up and I get 23. This was 21, 22, 23 out of 24. But I know if I look at all the possible values of my random variable, the probabilities have to add up to 1. In other words, 24 out of 24. I get 23 out of 24. So that tells me that I've missed one. Now that sucks when that happens, but at least I have that safety built in. What have I missed? I've missed something here. I can get a difference of 4 by also doing 6, 2. So this is in fact a 2. Now they add up to 1. Let's say here my check is that the probabilities add up to 24 out of 24, which is 1. Now it does, so I'm happy with that probability distribution. Now I also want to calculate the expected value. So the expected value of x is simply the number times the corresponding probability added up. So I just go down the line, 0 times 4 over 24, and I'm not bothering simplifying this at all. Plus 1 times 7 over 24, plus 2 times 6 over 24, plus 3 times 4 over 24, plus 4 times 2 over 24, plus 5 times 1 over 24, not 12. 24. And now I have to calculate that, so I get out my calculator. Let's do it like this. Now I know 0 times anything is going to be 0, so I don't need to really put this one in. I have to start at 1. 1 times 7 over 24 plus 2 times 6 over 24 plus 3 times 4 over 24 plus 4 times 2 over 24 plus 5 times 1 over 24. And I get 1.8333 repeating. So it's fine to say 1.83. Now remember, the expected value isn't going to be one of my possible values of x. It simply gives me an indication of what is most likely to happen on average. If I do this experiment repeatedly, and I take the average of all those results, what is going to happen on average? And it's sort of between 1 and 2, which is confirmed by the fact that the probabilities of getting a difference of 1 and 2 are higher than the others. So it is sort of more central around this range of values. For number 8, a raffle offers a first prize of $400 and 3 second prizes of $80 each. One ticket costs $2 and 500 tickets are sold. Find the expected net winnings for a person who buys 2 tickets at random. So instead of our in-class example where we bought only 1 ticket, now the person buys 2 tickets, making it a little bit more complicated in terms of the number of possible outcomes. But we start at the beginning and work our way through like any other problem. Number 8. So I have to start with naming my random variable. So we're going to say let x represent the net winnings from buying and playing 2 tickets. Now the possible values of x, I have to be careful to cover them all, to make sure I get all of them in my list. So let's just write on the side here, I have 1 first prize of $400. I have 3 second prizes of $80 each, and that's it. And I also have a zero prize, of course. So what are the possible values? Well, let's go with the best case scenario. What is the largest value I can have for x? When x represents my net winnings, so it costs me $4 to play, and this is what I can win. So I have to subtract the cost from what I've won. Best case is I win first prize and second prize, so I win 480. Minus 4 would be 476. What is the next best? Well, let's stick with the first prize and run through the options. These don't have to be in order as long as I get them all. So one way of systematically working through this is, let's suppose I get first prize paired with everything else. First prize and second, first prize and nothing. That would be 400 only, minus 4, which gives me 396. So let's say here first, second prize. This is first prize and lose. What else can I have? That's everything that I can get with the first prize involved. I can have a second prize and a first prize, but I've already covered that there. Second prize and another second prize, because there are 3, which would give me 160 minus 4, which would be 156. So this will be second and second prize. And I can also get a second and lose with the other ticket, which would give me 76. So this will be second and lose. So if I look back, I have first with second, first with lose, second with first here, second with second, second with lose. Is there anything missing? Yes, I can have both tickets lose, and then I'll have negative 4 as my net winnings. So again, I have lose with everything. Lose with first, lose with second, lose with lose. So these are all the possible values of x. It doesn't matter if they're not in order, as long as I have them all. So the next is to find the distribution. So for that, let's take the various values of x, let's call it n, and let's look at the probability that x equals that number. And I have various numbers. I have 476, and we'll continue as we go. So now the probability, let's do the bottom first. I'm looking for all the possible ways of getting 2 tickets. Well, I have 500 tickets, and I can choose 2. How many ways can I get a first and a second prize? Well, there's 1 winning ticket that I have to choose, and 3 second prize tickets that I have to choose 1. So this is a little different because I'm choosing 2 tickets. Next value is 396, and that's just a way to represent the first prize and lose outcome. So now again, over 500, choose 2. I am selecting the one first prize ticket, and then how many losing tickets do I have? If I have 4 prize tickets, I have 496 losing tickets. Out of the 500, I have 4 that win, so 496 that I have to choose one from. Let's extend this line. Next value is 156. When x equals 156, it's just a way to represent the outcome of 2 second prizes. Out of 500, choose 2. Now I have to choose from the 3 second prizes 2. 76 is the next one. Probability is over 500, choose 2 again. I want to choose one of the 3 second prizes and one of the losing tickets. And last one is -4, representing the lose-lose. Out of 500, choose 2 for the bottom, and out of 496, choose 2 of the losing tickets. And I'm done. And that is my probability distribution. Now they want to know what is the expected value of x, my expected net winnings. So I'll write it out so the calculation is clear. I just go down the line. 476 is the first value times the corresponding probability. So it's worth in the beginning to write it out so that you remind yourself how the probability is calculated. Next one is 156 times 3, choose 2, over 500, choose 2 as the probability corresponding to this value. Next one is 76 times 3, choose 1, 496, choose 1, over 500, choose 2. I'll do the next one here, plus -4 times 496, choose 2, 500, choose 2. Now it's a little tedious that I have this 500, choose 2 at the bottom every time. It's nothing I can't handle. So let's see. What I would note to make this a little easier is that anything choose 1 is just that number. So 3 choose 1 is equal to the number 3. 496 choose 1 is equal to the number 496. So it makes it a little bit easier. But I'll still do it in detail to show that it will work. So let's go. 476 times 1 times 3, because these are choose 1, so I don't need to say choose 1, divided by 500 minus second function 5 for the choosing 2, plus 396 times 1 times 496 divided by 500 choose 2, plus 156 times 3 choose 2 divided by 500 choose 2, plus 76 times 3 times 496 divided by 500 choose 2. And instead of plus -4, I'll just say -4 times 496 choose 2 over 500 choose 2. So it's lengthy, so I have to go slow to make sure I have it right, and I get -1.44. -1.44. Let's interpret that as well. Even though the question didn't ask it in this case, it might very well ask to interpret the expected value. What does this tell me? The reason I do this is because it tells me something about the experiment that I'm trying to examine. So in this case, the expected value is negative 1.44, which means that if I were to play this over and over and over and over and over, and I take the average of all my net winnings from those games, I average negative 1.44. And the more I play, the closer I'm going to get to this average. Yes, I might win first and second prize the next time I play. But if I keep going, I'm going to lose enough times to slowly get me back to this average. So this means that we lose money in the long run. An average loss of $1.44 per game.